In today's lesson, we are going to be looking at exponential growth. So in this unit, we are looking at basically exponential functions, and this is one of the types of functions. It's going to be kind of similar to what you've looked at in previous years, where you looked at new types of functions like quadratics or linear functions, so to speak. So we're basically going to look at the general characteristics, how they look, applications of them, and then we're going to tie in the transformations that we've looked at previously with exponential functions. So that's going to be basically what we cover over this unit. So first thing, we're just going to kind of go through a little bit of an example to kind of get us introduced to exponential functions. So a type of bacteria grows so that it triples in number every day. On the day we begin observations, a little bit of a typo. On the day we begin observations, the bacteria has a population of 100. We want to make a table to show the population over 5 days, and we want to calculate the finite differences and indicate any patterns that we might see. Right, so day 0, there's 100. Day 1, right, it said it triples, so a day after day 1, it goes to 300. Day 2, 300, that triples, so now we're at 900. Day 3, that triples, so we're at 27. That triples again on day 4, so now we're at 8100, and then that triples for day 5, so 24,300. So that's the population after 5 days. Let's go through and find our first differences. So this is something that you would have done looking at linear relations. So looking at our first differences, there's 200, or there's a change of 200. Next one, there is a change of 300. There is then a change of 1,800, 5,400, and 16,200. So basically, we're just looking at the differences in each value from the one to the next. And we'll do the same thing, second differences. So first differences tells us it's not linear, which I think we kind of knew that because we're not looking at linear functions. But we can see that the first differences are the same. And if we go through and do the second differences, change the size of that. Go through and do our second differences, 200 to 300, or 200 to 300. Right, so that is a change. Oh, no, I missed it. That's not 300. Mistake. 600. That makes more sense. So now it's a change of 400. Change of 1,200. Change of 3,600. And a change of 10,800. So those are our second differences. And we see that the second differences aren't the same. Right, so that again tells us that it's not quadratic, which I think we knew, because again, we knew we're not looking at a quadratic relation. Right, are there any other patterns that we notice? Right? Well, one thing that we might notice looking at these is that it doesn't matter what table we're looking at or what column we're looking at, whether it's the population, the first differences, or the second differences. The values are always going up in a similar amount. And that similar amount is they're always tripling. So we see that the values are always tripling or being multiplied by 3 every time we go up. Right, and so if that is kind of what we see, right? If we see that kind of constant multiple, that constant multiplier, right, or it's going up by a multiple every time, that's usually an indicator of it being an exponential relation. Right, so you could say if the finite differences increase by a constant multiple, it is an exponential relation. Right, so if we see a constant multiple, so we see the values going up by a constant multiple, then we consider that an exponential relation. So let's take a second to graph our values now. Right, so if we graph our initial values, so we had 0 and 100, so somewhere down here, 0 and 100, 1 and 900, or no, sorry, it was 1 and 300. So go here, 2 and 900, 3 and 2700, 4 and 81, and then 5 and 224,000. About there. So if we graph those points, we get something that looks like this. And again, that's an indicative of a exponential function, that strong increase. Right? X was our days, Y was our population. So we can see this kind of exponential growth. Right? So when we say exponential growth, we see the values increasing. Next, we want to write an equation for this model, or to model this growth. Right? So we have to kind of think about the characteristics, or what's actually happening. Right? So start off with y, or you could use f at x, whichever one. Right? But what are we starting with? Right? Well, we started with 100. Okay, and then how did that change? Right? So we started with 100, and then to get to the next value, we multiplied it by 3. Right? It tripled. Okay, so if I could kind of draw a quick table, right? X, Y, we had 0, we had 100, we had 1 for day 1, we had 100 times 3 to get 300. On day 2, we still had that 100 times 3 to get 300, but then we tripled it again. So we multiplied it by another 3 to get 900. On day 3, we multiplied it by another 3, or it tripled again. So how do I represent this kind of pattern mathematically? Right? We see the only thing that's changing is we're multiplying by 3. So every day we add, we multiply it by 3. Right? Or whatever the x happens to be, that is how many times we multiply by 3. So when we multiply something by itself over and over again, that's the same thing as just having an exponent. In this case, we don't know what the exponent is going to be because we don't know how many days we're looking at. Right? So in this case, our exponent is going to be our x variable. And so the equation to represent this growth would be y equals 100 times 3 to the power of x. So that idea, or that general form, right, that is going to be our exponential growth formula. Y equals AB to the power of x. Right? So in these cases, in an exponential function, the x variable is our exponent. Right? Our A value is going to be our initial amount, or the initial population, or our starting value. Right? Our B value is going to be the growth factor. And because it's growing, it's going to be greater than 1. Right? So it's going to be saying it grows by a multiple of 2, or it doubles, or something along those lines. Right? That idea, whatever it's telling us it's growing by, or whatever multiple it's telling us it's growing by, that's our growth factor. Y just equals the future amount, or the future value, and X represents the number of times A has increased. Right? So we look back at that bacteria one, right? X increased 3 times, so 3 days, so it was an exponent of 3. Right? Now, sometimes it might not be as simple as that for the X value, because it might not be increasing by a day or 1 year or something like that. Right? So in some cases, we may have to calculate X, and then in that case, X is the total time divided by the time for one growth period. Right? So whatever it says, it the population doubles every 2 days. So the 2 days would be your growth period, right? Or if the value tripled every 5 years, 5 would be the growth period. So you take your time and divide it by 5. So it depends on the scenario. So we looked at a graph of we graphed our exponential growth. We see it here as well. Some characteristics of it. We see that sharp increasing curve, right? So we see a quickly increasing curve. And the first and second differences are related by multiplication, right? So we see these values changing. So it goes over 1, right? So that change in y, right, goes up 1, then 2, then 4, then 8 in this example. Right, so in this case, right, we see that first and second differences are related by multiplication. So we should see these values be multiples of each other. So we'll go into a couple of examples. So your sibling tells you a secret. You see no harm in telling 2 friends. After the second passing of the secret, 4 people now know the secret. You, your sibling, and 2 friends. If each of these friends now tells 2 new people, after the third passing of the secret, 8 people will know. If this pattern of spreading the secret continues, how many people will know the secret after 10 such passings? So I'm just going to draw a table quickly just so we can visualize what's happening. Right, X will be the number of passings. And Y will be the number of people. So after 0 passings, there is just 1 person, right? Your sibling. After 1 passing, you and your sibling know, so now there's 2 people. After the next passing, right, you tell 2 friends, so now there's 4 people. The third passing, 8 people now know. So if we think of our general formula that y equals ab to the power of x, we need to figure out what is our a and what is our b. So in our case, our a value is our starting value, right? So in that case, it's 1, right? There's 1 person, that was the initial person that knew. There's 1 person that knew at the beginning. Our b value is the growth factor. So what is it growing by? What multiple is it growing by? Right? In this case, we can look at our values and we can see that they're doubling. They're doubling with each passing. So what that means is that our b value would have to be 2. So now to figure out how many people will know after 10 passings, you could continue the table if you wanted to, or what you could do is you could go through, plug in your values, and because it's 10 such passings, right, that is going to tell us when x equals 10. So we're going to plug 10 into our equation. 1 times 2 to the power of 10, or just 2 to the power of 10, and we get 1024. So therefore, after the 10th passing, 1024 people know. Another example, looking at the growth of insects or the growth of ants or whatever it might happen to be. So an insect colony has a current population of 50 insects. If it doubles, or its population doubles every 3 days, what is the population after 12 days? So in this case, right, we want to find our a and our b value. Right, so if we go through, right, start off with 50 insects, it says that it doubles every 3 days, and we want to know what is the population after 12 days. So here we know our A value is 50 because that's our initial population. We know that our B value is 2 because it's doubling. And this one's going to be a little bit different. I'm going to highlight this part in green because it says it doubles every 3 days. So that means that our X value is actually equal to our X over 3. Because the idea is that because it doubles every 3 days, the number of increases is going to be X divided by 3. So if I go and I plug this into my equation, y equals not A anymore, 50 times 2. Now it's not to the power of X, it's to the power of X divided by 3, right? Because that will be how many growth periods there are. So in this case, it is 50 times 2 to the power of 12 over 3, right? Because we're looking for the population after 12 days. We get 50 to the power of 2, or times 2 to the power of 4, or 12 divided by 3. When we do this calculation, we should get 800. So therefore, after 12 days, the population is 800. So small calculation that we had to do beforehand to make sure that we got the proper number of increases. For B, the insect colony is actually full of giant intelligent mutant insects. They plot that they can overtake the Earth when their population reaches 1 billion. When will we meet our doom? Or basically, when will our population reach 1 billion? So in this case, we're going to take our formula. So y equals 50 times 2 to the power of X divided by 3. Because we're looking for the population when it reaches 1 billion, that's our future amount. So we know that y is going to equal 1 billion. So 1, 2, 3, 1, 2, 3. Now my goal is to try to isolate for x. And this is where it's going to be new, right? Because you haven't really learned how to solve for x when x is the exponent. But we're going to try to get there first, right? So we're going to get rid of the 50 like we normally would. We're multiplying by 50. So we're going to divide both sides by 50. One side will cancel out. We're left with 20 million equals 2 times x divided by 3, or 2 to the power of x divided by 3. So this is basically saying 2 to the power of something divided by 3 equals 20 million. Now, what we can do, and this is going to be something new, so to basically bring an exponent down, right, to remove it so it's no longer the exponent, we're going to use something that is called logarithms. So logarithms are kind of like the inverse of exponents. So I'm going to take the log of both sides, and this is basically a button on your calculator. So the log of 20 million will basically give us a number. I'm going to do the same thing to the other side. I'm going to take the log of 2 to the power of x divided by 3. And there is a property when we're dealing with logarithms that this exponent, when it's log of a base to an exponent, this exponent can actually come down in front. So this is actually going to be equivalent to log of 2 million, or 20 million, is equal to x divided by 3 times log 2. Now log 2 and log 20 million are just values, so I can actually now continue to solve for x by dividing both sides by log 2. So in this case, I get one side will cancel out, sorry. I end up with log 20 million divided by log 2. I get 24.25, and that is going to equal x over 3. Now, last thing to do to solve for x is move the 3 up. So I'm going to multiply both sides by 3. One side cancels out, and we get 72.76 equals x. So that means that it's going to take 72.76 days before the population of mutant insects reaches 1 billion. Right, so new concept here of using logs to cancel out or to bring the exponent down to allow us to solve for the missing or the unknown variable when it is an exponent. Now, sometimes with exponential growth, we might not be given the growth rate as a as a factor, right? So we might not be told that it's doubling or tripling or quadrupling. We might be told that it's growing by a certain percent. And if we're told that it's growing by a certain percent, that's the exact same thing as saying that it's growing by a factor, right? So if the exponential growth is given as a percent, we would use a slightly different formula. Y equals a 1 plus r to the power of x, right? So y or a is still our initial amount in population. R is our growth rate as a decimal, right? So we would be given the growth rate as a percent, and we would have to turn it into a decimal. Y is still our future amount or value, and x is still the number of times a has increased, and we would still calculate it based on the the total time divided by the time for one growth period. So the same formula we would have used with the previous formula, we would still use it here with the growth given as a percent. So the only thing that's changed is that b value. It's no longer b, it's 1 plus r. So in 2005, there were only 285 Pittsburgh Penguins fans in Oakville. The number of fans increased by 75% per year after 2005. This is when Crosby was drafted, so obviously you get a good player, your fan base goes up. So how many fans are now, geez, another typo. How many fans are now in Oakville in 2014? So this one is slightly different because we're given the growth as a percent. It's increasing by 75%. So this type of scenario would still indicate an exponential growth. A couple other things to highlight. 285 fans in 2005, and we're looking for how many fans are there now in 2014. So I'm going to just write out my known values. So I know my initial value is 285. My R is 75% or 0.75. I don't have to do anything for my X value because it's increasing per year, right? So if my X value would be X divided by a growth period of 1, or X divided by 1, is just X. So I don't have to worry about anything with that. So I really just need my A and my R value in this case. There is one other thing I do want to take into consideration, right? Because we're looking at 2014 and we're looking for the growth after 2005, this only means we're looking at a growth over 9 years, because it's been 9 years since 2005. So I'm going to take all that information, plug it into my y equals a times 1 plus r to the power of x. Y equals 285 times 1 plus 0.75 to the power of x. Actually, in this case, we now know that x is 9. So y equals 285 times 1.75 to the power of 9. And we get 43,871.99. So therefore, 2014, there were 43,872, we'll round up, fans. Right, so same idea, same kind of calculation. We just had to add our percent to 1 to determine what the growth is. So again, we're not given a b value. We're not told like multiplying or doubling or tripling. We're given a growth as a percent. So similar idea, same type of calculations, just one small change in that b value. If we had to determine how many years it would take for there to be so many fans, we would do the same thing using logarithms, like we did in the last example, to determine or to move that x or that exponent down, and then we would solve. So very similar to what we did here. So that is going to be kind of the new thing, right? It's a new type of operation or way of canceling out exponents in this case. So that will be something you might have to review or practice. But other than that, it's just identifying the A and the B or the R value.